Welcome to part 2 of an exploration of the binomial theorem and how multiplication and counting are related. You might notice that things are looking a little bit different, sparser. That's because my computer died about 5 seconds before I finished part 2 of the video. But that's okay, we'll go along with it anyway. So, when we were wrapping up part 1, what we were talking about is how when you have this x plus y cubed, or really any exponent here, you get interesting patterns. So here we have a coefficient of 1 on x cubed, and then you have 3x squared, and then 1y, 3, and then 1x, 2y's, and x squared, and then plus 1y cubed. You get these interesting patterns. And how you can get that from something like x plus y times x plus y times x plus y. You can think about this as 3 choices between either x or y, right? Because when you FOIL this, you say first, would I like an x or a y? And then you say, let's multiply that by either an x or a y. And then for the final set of parentheses, you say, and then multiply that by either an x or y. That's what I mean when I have these drawn up here. Either you choose x, 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 maybe you choose y, 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 maybe you choose first 2, so x, then x, and then a y. But that'd be the same as if you chose an x, then a y, then an x. Or maybe you chose y, then x, then x. So you have these different ways of counting them. And that is the revelation that is bringing us into part 2 here, is that we can think about multiplication as a counting problem. Because you have these different options here. And then our question was, I have this total rearrangement divided by overcounting thing. What does that mean? Well, when we're thinking about this, let's look just at this x, x, y right here. So, what is this? We have 2 x's and a y. But the thing is, we don't care that these 2 x's are in these positions. And when we're doing counting, a lot of times it's easiest to find something called total rearrangement, which is to say, if you have three objects, like A, B, C, what is the total number of ways you can rearrange them? Well, you could do ACB, you could do BAC, you could do BCA, CAB, or CBA. So you have 6 ways. This is another way of saying the total number of ways to rearrange 3 things is 6. How did I come up with this? Well, we can come up with an algorithm. If we have 3 slots to fill, and we have things to put in them all, another way of thinking about this is that for the first slot, we have 3 options. Okay, let's say we go in the middle. So that's 3 different options. Then, for the next slot, we have 2 options. So maybe we go in the back. Alright, so now we've multiplied these 3 options by 2 options. And now, for the final letter, we only have one choice. We have 1 option. So the number of ways to rearrange 3 things is 3 times 2 times 1 is 6. If we had 4 objects, we could apply a very similar algorithm. We could say, first we have 4 choices, then we have 3 choices, 2 choices, and 1 choice, right? And that we could write as 4 options times 3 options times 2 options, and finally times 1 option. And this here, you might notice, it's the same as this, but then times 4, so 6 times 4, that's just 24. So we could say the total number of ways to rearrange 4 things is 24. But what's slightly different about what we're doing here with total rearrangements and these kind of partial rearrangements is that when we have our multiplication is commutative. So we don't care if we pick if we pick the first x, then the second x, then y, versus picking the second x, then the first x, then y. What I mean by this is, let's say they were all different objects. So we had a purple x, then a green x, then y, right? Or, well, excuse me, I just drew green y when I meant to do green x. So we have x, x, y. We when we're talking about total rearrangement, the total rearrangement machine is going to say, okay, this is one option. I see another option. It is called green X, purple X, Y. This is a new option, so I will count it as such. That is what the rearrangement machine is going to say. But the thing is, multiplication is commutative. We don't want to differentiate between these two options. We don't care if we have a green X, a purple X, and a Y versus a purple X and a green X and a Y. To us, it's the same thing. And if we take this back to our options machine, our options algorithm, that seemed to work pretty well. If we think about this, what we're saying is we have ABC, right? We have the 6 options, but we're saying count A and B as the same thing. Let's think about what this would mean for the number of options that we have. Well, one way of thinking about this is to think of, instead of placing A first, place C first. So we have the 3 options, and if we're putting C first, that means that we have 3 different options for where C could go, right? So maybe C goes into the 2nd place. So that was 3 choices that we had, 3 options. Now for A and B, though, we don't really care where they go, right? So a way of thinking about this is that once you have A and B, you do have your 2 times 1 more options, but then you also divide by those 2 and 1 more options, because you don't care if it looked like this or if you rearranged A and B so that you had the A and B in different places, because you want these to be the same. You want them to equal each other. You want them to not be different. So one way of thinking about this is to have the same as you had before, but then to divide by the number of ways you can rearrange just this B and just this A. So 2 times 1. Now before we go further, I just want to say that this sequence here of decreasing multiplications, this is so prevalent and useful and common in mathematics that we've given it a name. This is called the factorial. So 3 times 2 times 1, this is 6. This is also 3 factorial, which we write as 3 with an exclamation point after it. If we have 4 times 3 times 2 times 1, this here is 4 factorial. And this right here, 3 times 2 times 1 divided by 2 times 1, that would be 3 factorial divided by 2 factorial. Factorial is a tool created by mathematicians to count how many ways you can rearrange something. And then here what we've done is we've extended this tool to say, alright, this is the total number of ways we can rearrange it, but hey, some of these are the same as each other, so let's just say total rearrangement divided by the number of different ways that these equal things can be rearranged, to find the total number of ways that you can rearrange them without really caring whether the A or B is in a certain place. Alright, now that we have that, let's tie this back to multiplication, because there's one more key revelation that we need to have. So if we have, right now we're accounting for how much overcounting we have to do for x. Pardon the bad pun, please. But what about y? Well, in this x cubed case, right, with 2 x's and 1 y, we don't actually have to do this because there's only 1 y. But imagine an x to the 4th power case. There's going to be one option where you need to pick 2 x's and 2 y's, right? So you can either have x, x, y, y, or maybe you have x, y, x, y, or y, x, x, y. You'll have all these different options, and it'll go on and on and on, right? But you're going to need to not only, so you're going to find the total rearrangement, but then you not only have to overcount for x, you also have to account for how many ways you can rearrange y, which in this case is the option of swapping them. So what we need to do is we need to also account for y, and even in the x cubed case, you see when we have 2 y's, that does become important. So we need to not only divide by how many times x can be overcounted, but also divide by how many ways y can be overcounted. Because in reality, what we want to do is to have 3 different objects. So if we have the 4's case again, we want to say, okay, we have these 4 different objects, A, B, C, D, but 2 of them are the same, A and B. And then also, these 2 are the same, C and D. The total number of ways you can rearrange this is 4 factorial, 4 times 3 times 2 times 1. But then we want to say you can also divide this by how many ways can you rearrange just the oranges, just the x's. Well, that's 2 factorial. But then you're also going to say how many ways can you rearrange the purples, the y's, for multiplication? Well, that's also going to be 2 factorial. And when this comes out, you get 4 factorial is 4 times 3 times 2 times 1 is 24. Divided by 2 factorial, well, that's just 2 times 1, that's 2. Times 2 is 4, which equals 6. So this is a clue that if we're raising x plus y to the 4th power, the coefficient when you have x squared times y squared is going to be 6. That's really cool because we didn't actually FOIL any of that out. If you want to try, if you want to FOIL out x plus y times x plus y times x plus y times x plus y on paper, highly recommend you pause the video and go ahead and do that, because you will get 6, and that's what's so cool about this. It's a tool that lets us calculate the coefficients without doing the multiplication, because the multiplication gets pretty hairy. It gets quite unpleasant to do after you're raising it to the 99th power or something. You wouldn't want to do that. So we have this tool. Let's try to generalize this tool so that instead of having numbers here, we put variables in. And that's what's going to make this become the binomial theorem and become super awesome and super cool. So let's define some things here. Let's call a variable n. Let's say this is the exponent. Let n be the exponent. So again, tying back to multiplication, this means if we have x plus y squared, then that would be the same as n equals 2. If we had x plus y to the 5th power, that would mean n equals 5, right? And then we need one more variable if we're talking, so this differentiates between what the exponent is. The second variable here, k, we need this to differentiate which coefficient we're on. So in this case, let's say let k be the number of x's. And what do I mean when I say the number of x's? What I mean is, for the x plus y cubed example, for example, if you have 3 x's, so the x cubed, then k would be 3. If you add this x squared y, then k would be 2, because you have a power of 2 on your x, and then our formula should spit out 3 because that's the coefficient. If you pass in n equals 3 and k equals 1, so you have still cubing it, but now you only have 1x, so this term, then it should pass out a 3 for this coefficient. And if you say k equals 0, it should give you a 1 because there's a coefficient of 1 on the y cubed. So we can also say, given this information here, we can just say also that it comes out of this that the number of y's, because we're going to need the number of y's for overcounting for the y's. The number of y's is, well, there's this pattern here that we notice where you have a decreasing number. So you have x cubed and then x squared y and then xy squared y cubed. At every point, the total sum of the powers has to equal n. And if you think about it from the foiling perspective, that makes a lot of sense, because you choose either x plus y in all of your options. Well, it makes sense that the total number of x's that you choose plus the total number of y's that you choose has to be the total number of options that you had, the total number of picks that you made, otherwise known as n. So if the number of x's plus the number of y's has to equal n, that means that the number of y's is going to be n minus k. With all of this in place, we're ready to get ourselves a formula for what the coefficient is going to be for any of these different terms. So let's write it out. The coefficient for the number of x's, so for example, x squared times 1y, given the cube, n equals 3, what's that going to be? Well, we can write it down now. So we're going to have the total number of ways we could rearrange three things, again, but we're going to keep it abstract and call it n factorial instead of 3 factorial. And then we're going to divide by how many times we have to overcount for the x's. And, well, there are k x's, so the number of ways to rearrange those k x's is k factorial. And if we divide by the k factorial, what is that going to do? Well, dividing by the k factorial is going to remove all of those options from the total rearrangement, so it's going to make all of those x's count as the same thing. And we also have to divide by the rearrangement for the y's. If you remember, the number of y's that we had is n minus k, so here we're dividing by n minus k factorial. This is so useful, this function here. We just derived it, but it's useful everywhere. This is called the n choose k function, and sometimes mathematicians like to write it as n on top and then k on the bottom in tall parentheses here. But this function talks about total rearrangement if a certain number of your elements are the same, if they look the same, if they're just equal somehow. And in our case, multiplication, the x's and the y's, we do want them to be the same because it's commutative. It doesn't matter if you choose one x then the other one, or the other one then the first. So this here will give us the coefficient. So, and this is where it gets really cool. One way of writing now, an abstract way of writing x plus y to the power of n, would be to say, okay, so n choose k, n is just going to be n factorial, so we're going to write out the coefficients. This is going to be n factorial divided by, well, k is going to start at n, so you're going to have n factorial, because you're going to have n x's to start with, so you're going to have n times n minus, well, k is n, so factorial, times x to the power of n. And to this you're going to add, well, n stays the same, but now k is n minus 1. So, sorry, you have n minus 1 factorial times, and then n, well, k is now n minus 1, so n minus 1 is just 1. So now you have 1 factorial. And then this is all times x to the, now you have x to the n minus 1 times y to the 1. And you can continue this, right? You could say now this is n factorial divided by n minus 2 factorial times 2 factorial. This is all times x to the n minus 2 y squared. And you could continue this down the line, right? And we can just finish this off by saying plus y to the n. Any kth term here, if this is the kth term, we know by our formula that the coefficient here will be n factorial divided by k factorial divided by n minus k factorial. And I say divided because we're multiplying in the bottom here, but we're doing multiplication at the bottom anyway. And then this all times x to the n minus k times y to the k. This is already super cool, and I'm just going to take it the one last step to put this into series notation so that we can say officially, and this, when I first learned about this, I danced around probably for 30 minutes. It was so cool, and I encourage you, if you're feeling excited, you can go ahead and dance also. So x plus y to the nth power, I'll just write it here, series notation, this will equal up to n for k starts at 0. We're going to have n choose k, otherwise known as n factorial, divided by, and then here we're going to have, so we could say n minus k factorial times k factorial, but it's just rearranging the terms. So we can say here k factorial times n minus k factorial times x to the power of n minus k times y to the power of k. This blew my mind. This formula is super cool, and this is what we've been building to over the past 2 videos. So I hope that your mind is very pleasantly blown as well. And that concludes this series of 2 videos on the binomial theorem.